Welcome, my friends. In this video, I'm going to be working through Google Sheets lab number 8, and this lab relates to hypothesis testing. So if you'd like to access this file, then you can find that in the link in the description. And once you've opened the file, if you'd like to edit the file, you will have to go to File and make a copy. And you can title this with perhaps your first and last name, and then Google Sheets lab 8. And once you make a copy, you should be able to edit this file. Now the first sheet of this file is titled sign dist, which is related to like the distance that someone can read a sign. And let me just kind of pull up the prompt about information related to this data set. So we have two different variables. We have the age of the individual in years, as well as the maximum distance that the individual can read a highway sign at night in feet. And so the National Highway and Safety Board indicates that after dark, drivers should be able to read a sign at a distance of 385 feet or more. So if it's 385 feet or a little bit more away, they should be able to read that sign. We're concerned that drivers over the age of 50 perhaps are not meeting this safety criterion on average. So we've taken a random sample of a number of people here, and we want to know if on average those people are not able to read the sign at 385 feet or less. And specifically, we're going to be testing this for the people who are over the age of 50. And we're going to do this by going through the 3 steps of the hypothesis testing procedure we've done in class, which is we're going to set up our hypotheses, we're going to calculate the test statistic and p-value using Google Sheets, and then we're going to make a decision and write a conclusion. Now, let's see here. Looks like, yeah, it's down here. I have the null and alternative hypotheses. So the null hypothesis would be that the mean is equal to 385, and the alternative would be that it is less than 385. So the first thing that we need to do is we need to kind of filter this data set so that we only have the individuals who are age basically older than 50. So let's go ahead and do that. So you can see the ages kind of are all over the place here, but we really want to only test this for the people age 50 or older. So we're going to go ahead and click anywhere inside the data set, and we can go to Data, and we can create a filter. And then I'm going to filter this by age, or not filter, I'm just going to sort it by age. So I'm going to sort this from A to Z. Actually, let's do it from Z to A, so that I've got all the people who are 50 or older first. And then if I scroll down, I can go ahead and just delete the people. I could just leave them in there if I wanted to, but I'm just going to go ahead and delete the people who are under the age of 50. So I'm going to click on this first one here, the 49, and then I'm going to hold down Shift, and I'm going to click in the last one and then press Delete. And therefore, all I have left is the people who are age 53 or older. Or I guess 50 or older, but the youngest age 50 or older was 53. Okay, from here, we can go ahead and kind of fill in this table. This is going to allow us to do our hypothesis test here. So first we need the hypothesized mean, which we're trying to test against the number of 385. So I'm going to put in 385 there. And then the sample mean is going to be the mean based on the distances here. So we're going to find the sample mean by using the average function. So I can click in E3 here and then type equals average. And then I'm going to highlight the numbers here. It already kind of knows which ones I want. But these are the ones. And then I can close the parentheses, and it's giving me the sample mean. Okay, so it seems like on average those people are, they're able to read a sign at 370 feet, but you know, we wanted to be at 385, but on average it looked like these people were only able to read it at 370 feet or so. Now the question is this, you know, good enough evidence to suggest that, you know, in the bigger, broader population of all adults age 50 or older, is this good enough evidence to suggest that, you know, all of them really can't on average read at 385 feet? We have a slightly small sample here, but we'll go ahead and go through the test and see if that is the case. Now we need to also calculate a couple other things here, because we're going to need to find a test statistic using this formula here, and that's going to require us to know the standard deviation S as well as the sample size N. So let's go ahead and do that right here. So I'm going to reference the exact same range here. All I need to do is change the function. So I'm just going to go into this cell here. I'm going to copy this. I'm going to go into this cell, and then instead of using the average, I'm going to change that to standard deviation .s for standard deviation of our sample. And if I press enter, that's going to give me the standard deviation. Look like it's about 57.9. And then I need my sample size. I think I can kind of count here. It looks like it is about 16, or I can use the count function. I'm just going to paste that average in there again and change that to the count function. And therefore, it's going to count and tell me, oh, I have 16 different observations here. Now, something that you might know about the one sample mean test is really in order to do this test, you have to have either a sample size of at least 30 or your data should be following a normal distribution. And so our sample size is not at least 30, so we should be verifying that we have a normal distribution. So the way we can verify that is by graphing the distribution of the distances here and making sure that it is normal. So I'm going to select all the distances, and I'm going to insert a histogram to assess the normality. So I'm going to go to Insert Chart, and then I'm going to change the chart type to a histogram down here. And here you can see that the histogram, we've got the distances here on the horizontal axis, and it does seem like it is an approximately normal distribution, so that is a good sign. So I'm going to go ahead and just kind of make this a little bit smaller. I'm not going to worry about changing the titles or anything here because I'm not really using this for display. It's just to make sure that we did have a normal distribution, and it does appear that we do. So then let's go ahead and calculate the test statistics. So we need to use this formula here. We need to take our sample mean, subtract the population mean, and divide by the standard deviation over the square root of our sample size. So let's go ahead and do that. So we'll do equal to, open parenthesis here. We need our sample mean, which is 370.625, minus the population mean, which was stated as 385. That's what we're kind of testing against. And we're going to divide that by the square root. So we'll use the square root function sqrt. Actually, we don't need square root yet. We need it needs to be the standard deviation divided by, and then we need the square root, and this needs to be in parentheses. This divided by the square root of our sample size, which is 16. And that should get it for us, and it looks like it does. We have a test statistic of about -1, or -0.99. And now we can find the p-value using the t.dist function. So the t.dist is going to give us the left tail probability being less than this test statistic, and we do need the left tail probability because we have a left tail test. So that is going to be the correct one there. The x value is going to be the test statistic. We can do comma. We need the degrees of freedom, which are one smaller than our sample size, so that is 16 minus 1. And then cumulative we will select as true always for this to get a probability. Now this is going to give us the left tail probability. If we wanted the right tail probability, we would have to use 1 minus this, and you can see we just get the complement. Or you might have to multiply it by 2 for a two-tailed probability. But we need the left tail, so this is what we need. We can press enter, and we get the p-value of 0.1682. And then from there, you would make a decision and draw a conclusion. We're not really going to write that out here in Google Sheets, but I've kind of written that out here. So since our p-value is greater than any commonly used level of significance, like 0.05, we had a p-value of 0.1682 or so. That value is bigger than 0.05. We would be failing to reject the null hypothesis. Remember, the null hypothesis was that they could see it at 385. So we are not rejecting that claim, right? So we say there's not enough evidence to suggest that the mean distance an adult over the age of 50 can see a road sign is less than 385 feet. This probably should say at night, because it was really it was testing at night. Okay, so even though our sample did have a slightly smaller sample mean than the 385, it really wasn't significantly different enough for us to, conclusively say that they can't see it, and when it's at night, they can't see the sign at less than 385 feet, right? It was not good enough evidence to suggest that it was less than that based on this sample. All right, that completes this tab. So now we're going to go to the error simulation, which I think is kind of an interesting thing here kind of going on. So this is trying to test, what percentage of published results will actually be correct versus incorrect based on a few different assumptions. Now, I highly encourage you to watch the Veritasium video that's linked in the description of this video, or at least maybe just like the first 3.5 minutes where they kind of discuss this whole idea. But basically the idea is that with a couple of assumptions here, we can actually verify that somewhere in the realm of 30% of published results are going to be basically untrue. And that's even when he says in the video, even when the system is working properly, but even when people are using other techniques, like they're trying to p-hack or have multiple dependent variables, sometimes the percentage could be even worse. So we're going to try to verify that here using this little simulation. So one thing that was stated in there was that typically it's going to be a lot more common that your null hypothesis is true than your alternative hypothesis. So the null hypothesis is like your default position, and more likely than not, in many cases in real research, it's actually going to come out that the null hypothesis actually was true. And the split that he gave was a 90-10 split. So 90% of the null hypotheses were true and 10% of the alternatives were true. And we're going to do a simulation here with 1,000 studies. That's also what he shows in the video. He shows like a simulation with 1,000 studies, or not really a simulation, but just kind of the result with 1,000 studies. And therefore, if we have 1,000 studies and 90% of them are going to be a true null hypothesis, that's going to create 900 true null hypotheses. But I'm gonna code this in here. I'm going to do equal to the number of true nulls would be 1,000 multiplied by 90%, and that's going to give me 900. Or the number of true alternatives is going to be the 1,000 multiplied by the 10%, and that would be 100. Now, we're going to talk about something called statistical power here, which you may or may not be familiar with, and that's going to be important to this analysis. Statistical power says that, if the alternative is actually true, what's the chance that we actually reject the null in favor of the alternative, right? So the statistical power, he says in the video that typically this is set at around 80%, although sometimes it could be less, but we're going to set it at 80%. So that means that if the alternative really is true, there's an 80% chance that we actually figure that out. And so we're going to set that at 80%. And typically the alpha, which is the level of significance, this is the type 1 error rate. That's saying that if the null is true, the chance that we reject it, or the chance of a false positive, we're going to set that at 5%, which is kind of the typical value. We're going to leave this blank for now. We're going to put this as 2% later, but we're not going to worry about that now because we don't really need it. But we will use that a little bit later, but I don't want to put too many things down here until we really need all the values. So we don't really need this one, so I'll enter that a little bit later. Now we'll do a simulation here with 1,000 studies. So I'm going to number the values here from 1 to 1,000. But to do that, I have to add some additional lines here. So if I scroll down to the very bottom, I'm going to add 1,000 more rows. And I'm going to scroll back up here. And I'm going to enter in 1 and 2 into these first two cells. And if I highlight these, I can click these and drag these down. Now this is going to take a little bit of time to drag that far down, so this is maybe not the most efficient method. I'll show you two ways. So one way, I could just drag this all the way down, but you can see it takes a little bit of time to get down 1,000 cells. So what if you're doing 10,000 or 20,000, right? So maybe this wouldn't be the most effective way. That is one way to do it. But another way to do it would be to actually, instead of doing 1, 2, do 1 and then do equals, and the second cell could be that number plus 1. And therefore, when I click on that cell A12 there, I can just scroll down all the way to cell 1,010, hold down Shift, click on 1,010, hold down Control, press Enter, and that will copy all those down. So I mean, whatever way you want to do it, this is a little bit more efficient, but either way would be fine. So I'm going to scroll back up to the top. And then here we need to basically run the simulation. So the simulation is going to be for every one of these studies, we either are going to have a null hypothesis or an alternative hypothesis. One of those is going to be true. We'll have 900 true null hypotheses and 100 true alternatives. And then for each of those, we're either going to have basically a false positive, a false negative, a true positive, or a true negative. So let me pull up this document again to show you kind of where I kind of describe each of those results. So if the null hypothesis is true, which is going to be our first column there, we could either have a false positive or a true negative. So what does that mean? Well, we could have a false positive. That would happen if you rejected a true null hypothesis. So if the null is true and you reject it, that's what we call a false positive. And the chance of that happening is determined by our level of significance, or alpha, right? Or we could have a true negative, which would be if you do not reject the null hypothesis when it's true, right? So we basically have two different results here for our first column. We could either, if the null is true, we could either be rejecting it. That would be a mistake, right? That would be a false positive. Or we could fail to reject it. That would be the right decision. So that's either a false positive or a true negative. Whereas if the alternative was true, then we actually have two different possible results. So if the alternative is true, then you should be rejecting the null. So you have the possibility of a true positive, and that's going to be determined by that statistical power that we set at 80%. Or we could have a false negative, which would be if we fail to reject the null hypothesis when it really should have been rejected. So I know it's a little bit confusing with all the wording here, but hopefully you get the idea. There end up being these four different possible results. Depending on which hypothesis is true, you're subject to basically two possible outcomes. and the chance of those outcomes occurring is determined by either alpha or the power, depending on which case you're doing. So let's first let's talk about the true null right here. So if the null is true, we could either have a false positive or we could have a true negative. So the way we're going to do this is with an if function. And we're going to generate a random number from 0 to 1. And the way to generate a random number from 0 to 1 is to use the rand function. So the rand function, if I just do this here, the rand, if I highlight it here, it should show you, it's just going to calculate some random number from 0 to 1. It looks like I got 0.0509, or it'll change again once I press enter. But it's going to generate a random number from 0 to 1. And the way we can generate to see if we have a false positive or not is if this number is between 0 and 0.05, that's kind of in the range of alpha, meaning we have made a type 1 error, right? There's a 5% chance of making that type 1 error of the false positive. So if the random number that gets generated here is basically from 0 to 5% or 0 to 0.05, that's going to represent a false positive. So if this number is, I'm going to say less than my alpha here, and I'm going to need to press F4 on that because I'm going to want that to always be referenced when I drag this down. But if that number is less than 0.05, the random number, if it's less than 0.05, we can treat that as we have basically made the type 1 error. And so this would be what we're going to call a false positive, right? So that's my second argument, comma, false positive, if it's true. If it's not true, that means I'm not in that 5% chance of making the type 1 error. I didn't make the error. That means I must have had a true negative, right? I must have had a true negative. That must have been that I did not reject the null hypothesis. So then I can go ahead and I can close the parentheses and press enter, and I'm going to get a random value. I'm not going to continue the fill now because we're going to modify this in a second. But you can see here I got a true negative. So that was like a 95% chance of that happening. 5% chance I could have had the false positive. Now, if I was to drag this down, this would actually generate, it would generate 1,000 different results here. But I don't want 1,000 results. I only want actually 900 of those results, right? So I'm going to want to have a way so this kind of filters so that it only is going to create a result if it's in the first 900. And the way I can do this is by using another if function. So I'm going to put an if function at the beginning here. And basically, if the study number is less than or equal to that 900 as an absolute reference, I'm going to F4 that. Then I want to generate the result. So I'm going to do comma, and then if that is true, if the study number is less than or equal to 900, then we're going to generate the result, which is the entire function we just did. And then if I go to the end of that function, if that is not true, meaning the number actually must have been bigger than 900, then I'm just going to put in an empty quote. So if I do double quotes there, that's going to represent basically no outcome. And then if I close the parentheses there, it's going to give me a result here. And now if I was to double click here, now I can see when I scroll down, I get results for the first 900, but any of the ones after 900, there is the cell still has content in it, but it is not giving me any result because this number is bigger than 900 now once we get down here. So it's not going to generate any of those results, right? All right, now we need to do a very similar thing for the other column here. So I'm going to just copy and paste this because it's very similar. So I'm going to copy that. I'm going to double click on this cell. I'm going to paste this, and then I need to modify this a little bit, right? So now I'm going to worry about this part first. I'll worry about, actually, this part shouldn't actually need to change, right? We're still referencing that study number and want to know if it's less than, I guess it's not 900 now. It needs to be less than or equal to 100. So I do need to change that. So let's change that to, that would be B5, wouldn't it? And then now here, instead of referencing the level of significance alpha, I need to reference the power, right? The power is if the alternative is really true, which is true here, the chance of actually rejecting it, right? And so now we're going to reference the power, which is B6. And basically now if our random number is less than or equal to or just less than 80%, then that means, oh, we actually did reject the null hypothesis when we should have, right? We were in that 80% chance camp, right? So if that random number that's been generated is less than 80% or less than 0.8, then that means, oh, we've made the correct decision. We have actually rejected the null hypothesis. So that would be actually a true positive in that case. So I'm going to change this from false positive. Now it's going to be a true positive. And if that's not the case, meaning I generated a number like between 0.8 and 1, then I would have been making the other type of error, which is what we call a false negative. This is what we call the type 2 error sometimes. This would be the false negative. And if I press enter, that should give me a result. Looks like I got a true positive here, and I should be able to double click here, and that should generate only 100 results. And there you see I have 100 results. Now, I know that the way the simulation has worked is slightly misleading because it almost looks like this first row here is related to the same study, but this is like study number 1 through 900 right here, right? Which are all when the null was true, and then we have an additional 100 studies. So like these are not like related or paired together, right? This is one study and this is a separate study. So I know it can be a little bit misleading with considering it can almost look like this is just the first study, but maybe you consider this starting at like study 901 or something, right? All right, so now we have that result there, we can go and kind of summarize some of the results. So we want to count how many true positives, true negatives, false positives, and false negatives that we have. So we can do this by using the COUNTIF function. And I want to count values in this entire table. So I'm going to hold down Control and Shift, press the down arrow to get to the bottom, and then the right arrow once. And then that's going to basically highlight this entire range. I'm going to press F4 because I'm gonna copy this down in a second. I want this also to apply to these other ones, right? And I only want to count this, if I do the comma, I only want to count this if the criteria is that I want it to be a true positive. So since I've typed true positive in this cell, I can just simply select this cell. I could type it out in quotes, but since this is right here, I can just select that cell. Close the parentheses, and it looks like I had 80 true positives. Now these are automatically re-updating every time I enter a cell, but based on the current iteration here, I had 80 true positives. And now I can just drag this down to the other ones, and then it's going to give me how many true negatives, how many false positives, and how many false negatives. Now you can start to ask yourself, okay, why do I have so many true negatives? Well, the reason why I have so many true negatives is because, well, first of all, true negatives can happen when you have when the null hypothesis is true, which happened 90% of the time, right? So there's a pretty good chance that I could have a true negative because that's 900 of the studies that are possible to have a true negative, and 857 of them we made the right decision, right? Whereas the other 43 we made the wrong decision. So these are both related to the null hypothesis. These ones are actually related to when the alternative was true, right? When the alternative was true, those are the 100 there, right? So these ones add up to 100, and these ones also add up to 900 actually. And if we want to know the percent that are wrong, then we would sum up the ones that are wrong. So sum up the ones that are wrong, which are these two, and divide by the sum of all of them, right? So if I go ahead and I close this and press enter, it looks like about 5.7% were wrong. I'm going to change this to a percent form so we can see this in percent. And you can start updating cells, and you can see how this changes. It's somewhere in the realm of about 5%, 5 to 7% or so. Okay, but what we're really interested in is not what percentage of the studies in total are wrong, but the percent that are actually published who are wrong. So not all of these are going to get published, right? So we stated before, or I mentioned this before, that a lot of the negative studies are not going to end up getting published. So we're going to assume that all of the positive studies are going to get published, right? If you actually test a hypothesis and your research hypothesis is true, your alternative is true or appears to be true, you're going to be probably publishing that result in the vast majority of cases. So we're going to assume that all of the positive results, which would be these ones, right? Those are all going to be counted or published, right? So I'm going to copy those over. I'm going to do equal 72 there. And for the false positives as well, we're also going to publish all of those. So all the true positives and false positives are going to get published. Now, what about the negatives? Are we going to publish the negatives? Well, a lot of times the negatives are not actually published. If you kind of like if you didn't reject the null hypothesis, then your results are not really all that interesting. You're just kind of upholding the status quo. It's not really all that interesting, right? So many cases those are not actually published. So for that reason, we're only going to put in here, we're going to put in 2%, which is the number that was used in the video, suggesting that, about 2% of the negative results are going to be published. And we can find that calculation by taking the number of, here we have true negatives. So by taking the number of true negatives here, and only 2% are going to get published, so I'll multiply that by 2%. And same thing here for the false negatives. I'll take the false negatives, there's 19, and multiply that by 2%. And it looks like we only get 0.4 there, right? Now, these numbers as decimals maybe doesn't make a lot of sense, so maybe we want to round these numbers. So we can round these numbers by using the round function. So I'm going to put that around here because you can't really publish a partial study. So I'm going to round that, And I'm going to round this one as well. And that one is in most cases actually gets rounded down to 0, right? Because 2% of the false negatives is like 0.4 or so, right? In some cases it'll probably be 1, but yeah, in most cases you can see there that one is, yeah, okay, I got it to be 1 at one point, but in most cases that's going to actually end up being 0 of those false negatives get published. Okay, so let's tally up the total number of published results, which would be the sum of the numbers above. So there end up being, in this simulation, 128 published results. And what percent are wrong? Well, the percent that would be wrong would be all of the false ones, right? So I'm going to sum up the false ones, and I'm going to divide by the total number of published. And you can see here, okay, in this iteration, it's about 38%. I'm going to go ahead and add a checkbox here in H2. So if I go to Insert, and then I insert a, let's see here, checkbox, and now I can continue to press that and kind of see how that changes. So whereas the total number of studies that are wrong is only about 5 to 6%, the total number that are the total percent that are wrong is like closer to maybe around 30%, right? And I think the video said about 1/3 or 30%, 33% or so are wrong. And so this is kind of verifying that, right? If these assumptions are all true, then even with the system working properly, without people like doing things with their shading things with their research, actually we can expect to see about 31% or 35% of the published research to be wrong. So in the next part here, if you go on to do the kind of practice portion of this, first of all, I'm going to have you kind of extend this. I'm going to have you extend this so that you have more than 1,000, so that you can kind of change this. Right now, I can change this. I can change this to 500, and then these would generate less. But I want you to change this so that it'll work for 10,000. So that'll cause you to change a few things here. But also, I'm going to want you to kind of experiment with changing a couple of these assumptions. If we change some of the assumptions, like we change our alpha or the percent of negatively published articles, or maybe the percents here, how is that going to change the percent of the research that ends up being wrong? Because this is a solvable problem, right? If we start modifying some of these things that actually could be changed, maybe that would help to fix this problem, right? And specifically, the ones that really can be controlled here are going to be the alpha and the percent that are published of the negative results. So I'll leave you to kind of experiment with that. Okay, I think that is everything I wanted to discuss in this video. So hopefully this is helpful, and I encourage you to go ahead and try the practice portion of this assignment.